Hello, everyone. We have with us today Dr. Dan Deviri, co-founder and CEO of CarbonBlue, a promising Israel-based climate tech startup working on water-based carbon dioxide removal technology. Dr. Dan holds a Ph.D. in physics from Weizmann Institute of Science, as well as degrees in chemistry and biology. So in 2022, Dr. Dan founded CarbonBlue with Iddo Tsur, who now serves as the company's COO, with the stated goal of developing a high impact technology capable of decarbonizing industrial activities on a global scale. So, Dr. Dan, welcome to this podcast and thanks for chatting with us.
Pleasure to be here.
Thanks a lot. Can you briefly begin by explaining to us what CarbonBlue's CDR technology is and how is it different from the other CDR technologies already present in the market?
Yes, of course. So I think that before I say how we distinguish from other CDR technologies, let's talk briefly about what we perceive as the real challenge in CDR. Because according to the Intergovernmental Panel on Climate Change, in order to avoid the worst outcomes of climate change, the scale of CDR we will need to reach by mid-century, which is only less than 30 years from today, is about 10 billion tons of carbon dioxide per year. Just to get the scale, it's probably more than most things we can imagine that we produce. Let's say, for example, oil. Crude oil, the production of crude oil is about 4 billion tons a year of oil. Cement, which we build our homes from, another 4 billion tons, and steel, which is the key ingredient in most stuff we manufacture, it's 2 billion tons. So sum it all together, steel, cement, and oil, and you will get the scale of CDR that is needed every year. And this means that the challenge is not only to capture carbon dioxide from the atmosphere, because that is, I would say, simple. I mean, we can plant trees to do that, but we need to do that, and we need to find technology to do that in a way that would be highly scalable, that in only 30 years, we will be able to get to the gigaton scale. And we tried to develop our CDR technology along those guidelines. And to do that, we target water. Why water? Well, for starters, water holds most of the carbon dioxide in the carbon cycle. It means that if we emit a molecule of carbon dioxide, most of its life, this molecule of carbon dioxide would spend in seas and oceans. More than 90% of the time, 98 to be exact. If you look at a liter of seawater, there would be 140 times more molecules, more carbon dioxide molecules in this liter of seawater compared to the air. And this is our philosophy. We want to target water. We want to remove carbon dioxide from water, of course, in a way that will cause the water, like a sponge, to reabsorb back what we removed from the atmosphere. So the net effect is removal of carbon dioxide from the atmosphere. If we look, for example, at the largest CDR facility that is being built out there in carbon engineering facility in the south of the United States, which will at its full capacity will be 1 million tons per year. This is the facility the size of the Vatican. It is huge, and we cannot build tens of thousands of those worldwide. We need to get it more flexible. So that's what we do. We developed a reactor that can remove the carbon dioxide from water and integrate into existing water withdrawal facilities, from desalination plants to wastewater treatment facilities, agriculture, aquaculture, basically whatever moves water around, and it doesn't matter if the water is saline water or fresh water or anything in between. Our technology is quite different. It is based on two steps. In the first step, we mineralize the dissolved carbon dioxide in the water into a form of a mineral that contains the carbon dioxide, the carbonate mineral that contains the carbon dioxide, by adding material called lime to the water. We then take out this carbonate mineral from the water, and we can carry it around. It's a solid. It's very easy to handle, store, and transport. And we can get it to a site where we do the opposite. We take out the carbon dioxide from this carbonate mineral and regenerating the lime for further use in more capture cycles. The lime is also solid that is easy to transport. And the CO2 that is released in this process, we either utilize or sequester to achieve the result of the CDR at the life cycle level. We're the only ones that do that without using electrochemistry. So while all our competitors working with water, the engineered-based approaches working with water, are using electrochemistry to move the carbon dioxide around, we do not. And that creates some points of distinction. For example, we are the only ones that can operate on any type of water. That because electrochemistry requires the water to be conductive, and for the water to be conductive, the water must contain salt. So we are insensitive to the salt levels, and we can transport and store the carbon dioxide in a mineralized form, which allows us more flexibility in deployment, and also in usage of energy, because we don't have to remove we can capture carbon dioxide in the form of calcium carbonate, in the form of the carbonate mineral, 100% of the time, to maximize the use of the infrastructure and reduce costs. But the regeneration, which requires most of the energy, this is something we can do discontinuously when there is availability of renewable energy. And I guess that we all are aware of the intermittency problem of renewable energy, that we don't have renewable energy 100% of the time. Yeah, so I talked for almost 10 minutes uninterrupted. Yeah.
No, that's fine. So thanks a lot for giving us the introduction about CDR and about the relevance of it. One thought which comes to my mind. So apart from offsetting the carbon footprints, what are some of the economic use cases for businesses and industries to install your CDR technology on their premises? And also, which type of industries do you think are more suited to benefit from your solution?
Yeah. It's a great question. So, as you can imagine, if we leverage existing industries, we have to provide business incentives for the owners of those infrastructure to let us use the infrastructure. And the answer is that we have basically two pieces for our technology. One piece is the water-facing piece of our technology, what removes the carbon dioxide from water, and the gaseous carbon dioxide producing part of the technology, which is what liberates the carbon dioxide from its mineral form. And so if we take carbon dioxide from the carbon cycle and we sequester it, durably sequester it, we can get carbon credits for the voluntary carbon markets. But that's not the entire story. That's more the cherry on top in our case, because the technologies I mentioned, the two pieces of our technology can significantly benefit different industries. For example, in the water-facing side, desalination is an industry that suffers from the presence of carbon dioxide in the water. Because if you would remove the carbon dioxide from water prior to desalination, it depends on the specific use of the water and desalination targets, but you can reduce up to 10% of desalination costs by scrubbing off the carbon dioxide. And in desalination, where margins are very small, a 10% reduction in costs, it is very significant. The use of the treated water is heavily used in industry, and water contains not only the molecule H2O, but also a bunch of other molecules, including calcium and carbon dioxide. And those calcium and carbon dioxide molecules tend to associate together and create limescale, which is this white brownish residue.
Right.
This is a major problem in industry. And this is a composition of carbon dioxide. So, for example, one, I think, very universal advantage of removing the carbon dioxide from treating the water is that we soften the water. And we eliminate this residue and therefore reduce maintenance costs for any equipment that is in contact with water, industrial and domestic. Similar for the carbon dioxide side, many industries require carbon dioxide, and having a constant supply, local supply of carbon dioxide at their sites is a great advantage, and it is a great business incentive. So combining those two, we find that we can partner with different industries, ranging from desalination, aquaculture, power production, even oil and gas, not for EOR, just to make it clear, for other business use case, and more traditional industries like cement, pulp and paper, and many other industries. We can provide robust economic value beyond moving the carbon dioxide out. So that's our business philosophy, to create value for both sides of our process, both the water side and the gas side, and by managing the supply chain, which is pretty unique when you think about it, because if you would like to buy carbon dioxide now for industrial purposes, you would need to get some sort of specialized cryogenic truck or pipeline to transport it, and this is not needed in our case. So we can, by managing the supply chain, we can generate significant revenue for us and support the growth of the CDR industries and the circular economy, circular carbon dioxide economy industries that are emerging.
Okay, great. So what you're saying is that the CO2, since it's generated at the premise itself, like the whole cost of logistics of procuring the required CO2 from somewhere else, getting it transported, all of that also gets saved.
Yes, definitely. I mean, most of the CO2 in the world, if you want to buy CO2 for industrial purposes, let's say that you are, there is a nice anecdotal story, two anecdotal stories actually. One about Coca-Cola in the United States. In the United States, the supply of carbon dioxide is from carbon capture from ethanol fermentation facilities. There is lots of ethanol production in the United States because I don't remember if it's 5 or up to 10% of the gasoline in the United States is mixed with ethanol, and production of ethanol releases lots of carbon dioxide, very pure stream that is cheap to capture and monetize. So so most of the carbon dioxide that you have in Coca-Cola in the United States comes from ethanol fermentation plants. And during COVID, during the lockdowns, people didn't drive their car, and the gasoline consumption plummeted, and the market for ethanol also plummeted, and with it, the byproduction of carbon dioxide also halted. So people sitting at their homes couldn't buy Coca-Cola because there weren't any carbon dioxide for the Coca-Cola facilities. So this is just an example for how complex this seemingly very easy to get molecule industry around it. And it depends on where you are located. If you are next to, for example, the fermentation plant I mentioned before, then carbon dioxide is very cheap and widely available. But if you are on an island country where there aren't any ethanol fermentation plants or ammonia plants or gas refineries, natural gas refineries, the price of carbon dioxide can get to hundreds of dollars per ton. And this is more than a carbon credit. So this by itself, providing carbon dioxide from industry, a sustainable carbon dioxide that comes from the environment and is not added to the environment, can be a good business.
Right, that's great. So you also mentioned about circularity. So can you tell us how does your solution contribute to the circular economy in terms of deployment of your solution at the premises, and whether the infrastructure that you deploy is that portable, is that reusable, or like new infrastructure needs to be created for every new project?
Potentially, yes. It depends on the scale, because if you have, let's say, a power plant, hopefully low carbon power plant like a concentrated solar power or nuclear power plant that uses water for cooling, we are talking about a scale of hundreds of thousands of cubic meters of water per hour. And for that facility, it is unlikely for us to provide portable equipment because it is huge. But if we're talking about a relatively small industrial facility, we can provide the mineralization equipment in a portable form, as for example, plug-and-play container. You just have to connect it to the water infrastructure, and that at the end of life of the facility, there is no reason why you wouldn't recycle the mineralization units. Of course, up to maintenance and natural degradation, which takes long time. But yeah, it can be at small scale, it can definitely be portable.
Also, I wanted to understand, while checking the feasibility for deployment of a CDR technology for a particular project, what are the main prerequisites and the operational challenges that you evaluate?
I think the prerequisite is going to be that the water should contain carbon dioxide. We haven't encountered any water that does not contain carbon dioxide, but in some cases the concentration can be relatively small, which makes it less desirable, both less desirable and the incentives for deploying the technology smaller. I would say that content of carbon dioxide, amount of water, the co-benefits that are created by deploying the technology is a major factor as well, because we would prefer to deploy in industries where the incentives are stronger, like I mentioned before, and also the community support for it, because we don't want to deploy in places where the community is against it.
What could be the reasons why do you think a community would not support such kind of a project? Is it because of like some additional land is required to set up the project, and that's where you see a conflict of interest could come into play, or are there some other reasons?
No, I don't think that's the reason because the land area used is pretty small in our case. I think the main reason we've seen is more focused on a concern what would be in the future for with this deployment. I would give an example. In the United States, coal power plants use massive amounts of water for cooling, and theoretically, we can integrate with the cooling system of the coal power plant, and make from a bad thing, try to squeeze a little bit of good. But then environmental groups, and rightly so, can come and say, but if you use the water cooling infrastructure, you are strengthening the position of this power plant over here, and you make it very hard to change you make it even harder to change the status quo. So out of those grounds, this is mostly what we've seen.
Okay. And also, Dan, is the last question. So, what are your plans for deployment of the funds raised through your recent round? And congratulations for raising the investment. And
Thank
also,
you.
what are your plans for global expansion, and which countries do you think your technology could be, expanded to in the near future?
So first of all, thank you for the kind words. I think most of the money would go for scale up of the technology and piloting, because you might think that in a life cycle of technology, it starts small. You do it in a lab, maybe it's called breadboard validation, that you develop different components and check each component separately that it works. But the real expenses start once you are integrating it into a larger scale facility. And that's not because there is lots of open questions. I mean, there are open questions, but it's mostly because engineering tends to be more expensive the larger it is. So most of the funds would go for scale up, and piloting. The pilot I mentioned before, which may be, depending on how quickly we run it, it may be the largest water-based CO2 removal facility in the world, 400 tons per year. That's the scale of what we are building now.
Okay.
And in terms of global deployment, yes, I mean, we do want to deploy globally. The countries we see are, I would say, the intersection of two preconditions. One, we do want to see regulatory incentives for decarbonization technologies, because usually those incentives mean that we can that our financial models and business models are more robust, which brings us to the United States and Europe mainly, but also in countries that has lots of water and water infrastructure. For example, the Gulf countries like the United Arab Emirates and the other countries in vicinity, that they have lots of desalination. So that's another place we are focusing at, and also some places that have extremely cheap, or the potential for very cheap, renewable energy, and hydrogen and large hydrogen projects are being built up, which is Latin America, for example, and North Africa, because carbon dioxide at those places can become e-fuels, and this is also a market that we are targeting. I would say that those areas are our areas of focus.
All right. Well, thanks a lot, Dan, for sharing all this information with us.
Thank you. And I do want to use the time to say one more thing, share one more piece of vision of CarbonBlue. And I wanted to imagine a world without oil. Oil, we know it as a source of energy, and if we would have enough wind and solar, and nuclear, and other form of low carbon energy, potentially we can do without gas and oil, assuming that we will be able to decarbonize hard to abate industries like aviation and shipping if we use e-fuels, for example. But there is one more important aspect of oil that we tend to overlook, and this is oil as a source of carbon for plastics. And I guess most of us know that plastics is made of oil. And even if we would be able to generate enough renewable energy so we don't need to dig oil out of the ground for energy, we would still need it for plastics. And this is something also that we see as the potential future for CarbonBlue, is to provide carbon dioxide as a feedstock for anything that uses carbon, whether it be plastics or fuels or any other, or minerals or any other form that is currently being used in the industry without thinking about it. And you can imagine your car that you drive, there is a lot of plastics in that car. And I want you to imagine a future where you enter this car and the car is carbon negative because all the plastics is from plastics that is made of carbon dioxide we removed from the atmosphere, and the fuel that you use to run the car is e-fuel, meaning synthetic fuel that was generated from carbon you capture from water using CarbonBlue's technology. And this vision of sustainable future goes as much as it is low carbon energy, it is also low carbon dioxide. And this is what we do, and this goes beyond CDR alone.
It certainly is interesting. So basically, we see a lot of co-benefits along with the main process of carbon dioxide removal. There are a lot of other industrial uses also, and which in turn again help us to combat the environmental challenges. So point noted, and thanks a lot for sharing all this information again. And we wish you and CarbonBlue all the very best for your future.
Thank you very much, Akshay, and thank you for your good work.